Good evening. So I guess it's just one student today. So am I audible?
Yes, ma'am.
Okay, and you can see me also, right?
Yes, ma'am.
Okay, okay. So were you present in the last live session last Friday?
Yes, ma'am. I was present.
Yeah, yeah. Okay, okay. So pardon me if I forgot your name, but it's fine. So should we wait? Yeah, okay, okay. So mostly we'll be discussing about week two questions assignments from last year. And what I understand is that you guys need a bit of guidance on the topics also. So we'll be doing that today. Uh, we'll be taking up questions and the explanation behind it. We'll be discussing that in details also. Feel free to ask me questions at any point. You can interrupt me if I'm going fast. Definitely do let me know. And if you feel like you're not very clear about or you need more clarity on a topic, let me know also. Okay. So let's start with the questions. Just let me know if my screen is, I'm like presenting, just let me know if the PPT is visible or not.
It's visible, ma'am.
It's visible, right? Just tell me it's changing or not. Hmm. Is it changing?
No, ma'am. Yes, ma'am. Now it changes.
Just give me 1 minute, okay? I will. Okay, yeah. So welcome again. This is session two, live session two of this course, Interface with Biology and Medicine. And as mentioned, we'll be discussing these specific topics today, mostly on cloning, like different tools used in cloning, gene cloning, and also the different aspects of cloning that are used in biotechnology. So, many of you might be new today. I am Srishti Banerjee. I am from IIT Hyderabad. I'm a PhD student, and I'll be your TA for the rest of the course. Okay. So just like last week, what we did is I used to flash each question, and then we used to have a discussion on which is the correct answer, and then we would like come be on the same page. Like once everybody is on the same page, then we proceed to the next question. So it will be a 2 hour session. We will be discussing over 11 to 12 questions, a slightly experimental and larger questions. So it will take time. So feel free to ask me questions in between every question and if you want more clarity on a particular topic. Okay. So let's begin. So this is the first question. Yeah. So the first question, all of you can read and then I'll explain also. So it's mostly about cloning a parasitic gene in two different vectors. So what are vectors? Which is also known as plasmids. Plasmids are actually vectors. So they are useful in carrying the gene of interest into your target cell. So suppose you have a gene X and you need to transfer that particular gene to a cell which is Y. So for that you need a carrier for transporting it, and that is a vector or a plasmid. So here we have gene PVX. This is the name of the gene, and we have to clone it. In cloning means to develop multiple copies of one. So like developing a clone means that you need to generate multiple copies of the same thing. So you need to generate clones by in the these are the two plasmids. One is PET10 and another one is PUC19 by a primer-based amplification of gene followed by restriction, digestion, ligation to the respective vectors. So after cloning, you transform the recombinant vectors in a particular cell like BL21, DHF alpha. These are the name of the cells. Now you perform a colony PCR to confirm if your cloning experiment was successful or not. Next, you extract the plasmid out of it and confirm the colony and you send it for sequencing. So, in very brief, what is actually happening here? You have a gene, you have to clone it in a plasmid, and then you have to transfer it to a bacteria. And in between steps are like once you're cloning it then once you've cloned, you need to amplify it, and that will be based on primer-based amplification of the gene. Then once you have your respective number of copies of the particular gene, then you're you're performing a digestion or restriction digestion on it, followed by, so after you perform this restriction digestion, you have your small genes, that is the PVX in that particular vector, and you have a multiple copies of it. And then you ligate that target to another vector or the respective vectors that is. Like that, post cloning, you have to, now once you have a plasmid which has your gene of interest, you need to transform that into a cell so that it can grow and amplify. So that is done in BL21 and DH5 alpha. You need not worry about the names. These are just name of strains. And once that is done, you need to see that your cloning experiment is successful or not. And how do we do that? We do it with a colony PCR. Now, what is a colony PCR? Like you have a petri dish which has lawns of cells, colonies of cells. You take up one colony and directly extract DNA from it and perform a PCR to confirm that that particular colony has your gene of interest or not. So this entire story will completely depend. First thing is that you need to clone this particular gene in your vector. Like you need to insert this gene inside your vector. So the question is, suppose you have this vector P10 and you have your gene PVX, XYZ, whatever the name is. Now you need to insert this particular gene within this. So what are the restriction enzymes that you're going to use? So what do you mean by restriction enzymes? That which enzymes will cut this particular vector so that in that cut area, this gene can be inserted. So you have four options out of it. If like any one of you can just guess what could be which one could be the answer, possibly the answer. Use your chat box or you can just unmute yourself and tell me. Anyone? Anyone? Uh, Endel B, ma'am. B. Okay, fine. Anyone else? Prachi, now can you just unmute yourself and say why you feel that B is the correct answer, that Endel 1 and B, BAM H1? Why you feel so? So, I guess, Prachi, can you? Okay. So the thing is, how do we solve these kind of questions? Like they are saying that you need to cut this vector, insert it. To cut this vector, we need to see the different restriction sites that this vector has. So if I'll just yeah, zoom in this picture. These are your different this BGL3, XBA1. These are the different cut sites, and these cut sites mean that this can be cut by this particular restriction enzyme. Okay. So we need to find that out of these options, which one has common? Like a common pair which is present here also and here also. Like BTSC1, DRA1, this is not present here, right? NDEL1 is present, that you're correct, but BAMH1 is not present. So this cannot possibly cut this and we cannot insert it here. Out of all the options, if you see that, and same thing goes for hint 3 and DRA1. Hint 3 is still present, but DRA1 is not present. Okay. But NDEL1 and hint 3 both are present. So the correct answer for this is NDEL1 and hint 3. Why? Because this particular pair of restriction enzyme has sites in this vector. Sorry, ma'am, I cannot. No, it's okay. Prachi, don't be sorry for it. So it's fine. Okay. So is it clear? Like, how is this pair, like, why is this pair the answer and why not these four? Because this particular thing, this particular pair has its sites here. And so we are going to choose, or when you're going to perform this experiment, you're going to choose these two enzymes for this one. Clear? Or you want me to repeat? Is it clear to all the students present here?
Yes, ma'am.
Okay. Okay. So we'll move on to the next. We'll have more discussion on like this restriction enzymes, colony formation. We'll have more like today, most questions are on that only. So eventually we'll clarify more. Okay. Next question. Okay. So again, suppose you have this sequence of PVX101502. That is the same gene that we were discussing in the last question. And the sequence is given here. Yeah. So this is the sequence. Okay. Now you need to amplify the sequence before doing your experiments. By amplification, what we do, we generally do PCR, polymerase chain reaction. So what it happens is, suppose you have one, it exponentially amplifies it to a lot so that the copy number of it increases. So what is copy number? In biotech, copy number means that suppose you have one, you need to increase or amplify the number of that particular sequence. So it'll have more. So this is the sequence of your gene and you need to form, you need to prepare primers for it. Now, what are primers? Primers are like the nucleation event of any polymerase chain reaction. Like in order to amplify a sequence, I hope you are you're aware of central dogma. What happens is in replication, here we say amplification because it is amplifying, but the term is replication. Like you replicate whatever is present to you, and these yeah. So the next question, okay. Hmm. So the next question is, it's like a flowchart kind of a question that what is the process? How do you do gene cloning? Like what is the major steps in gene cloning into bacterial cells? So what is the thing? It is like you have a target gene that you want to uh, amplify or clone within a bacterial cell. So the process is first you take a vector. So let's just discuss that how this you can just see the four options and we can like have a discussion like what is the correct option. So yes, feel free to use your chat box and you can just have a look at the question, have your answers, and in 10 minutes the session will get over because of limitations in Zoom meetings. Then maybe you can all rejoin the same, just rejoin all this the same meeting link and we'll discuss the answer in that next session. Okay, so just have a look and what does. Okay, we have already have answer. Option C, Nidhi. Okay. Okay. 3 people are for C. Most of you are saying it's C. Okay. 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 So who was the first one to answer? Option C, Nidhi. So Nidhi, can you just elaborate like briefly that what happens in cloning? Like when we are doing, what are the different steps and why do you think that option C is the correct answer and not B, A or D?
Hello, ma'am.
Yes. Hello.
So basically, in cloning, we first take our gene of interest and we need the vector as well, and then we use the restriction enzymes to digest the vector and the gene of interest at the required point, so we get the ends, and then we need to get the two so that we can insert the gene of interest into the vector and then transform it into the competent cells so that using PCR we can grow the bacterial cells and amplify the gene. And
Okay.
that's why C is the option.
Yeah, so you absolutely correct. C is the answer. And let's see the process, like what exactly happens in a cloning. I have just taken a picture from internet. Yeah. So this is your sequence, like your entire DNA sequence. And this part where you see the two, you see a pair of scissors here. This is your exact sequence of interest, like which you want to incorporate within your target cell. And this is your vector or the plasmid. Now, a plasmid is known as the vector. Why? Because it carries this particular gene of interest from one point to the next point. So, this one point is where you are just inserting it, and the last or the end point or its destination is the bacterial cell within it. Okay. So, what happens is you have to cut this particular sequence with restriction enzymes, or you need to perform a restriction digestion of this as well as of the vector so that you can cut this and insert this thing within it. That is what is happening here. See that the green part of this gene is incorporated within this vector, right? So once it is incorporated within the vector, you have a plasmid or you have this vector which has your gene of interest. Then what is done? Then you prepare your cells. Like normally bacterial cells are not competent. Like by competent means that the ability to uptake a particular gene of interest or a vector. How? Through it actually there's a process through it the DNA or it goes through the membrane and it enters the bacterial cell. So you prepare your cells, you make it competent enough so that it can uptake the foreign gene or the plasmid that has your gene of interest. So within the bacteria, what will happen? That it will now multiply. You see here you're supplying this bacteria with your vector. Now this is like this and it will increase in number and from one you have n number of your gene of interest that is within the cell. So as I mentioned that you need to prepare your cells. So how do we generally prepare? Generally, we give a heat shock to the cell so that it forms some transient or short-lived pores in it from which the DNA can easily enter, like this plasmid can enter through it. So that is done by a heat shock. And in the next few questions, we will come into that we prepare calcium chloride competent cell. We'll get into details that how this calcium chloride is actually helping the particular DNA to get inside the cell. So is it clear that the how the process of cloning happens like from your gene of interest to increasing that particular gene of interest? How is it happening? Is it clear or should I repeat? I should repeat or is it clear? Clear. Okay. Okay. So yes, the answer is C. Okay. Okay. So we still have 4 minutes. Right? Okay. So we can discuss this question. So heat shock is the next question is heat shock method of transformation is done to transform the recombinant vector in the host system. What is the type of competent cells required for heat shock method? What are your answers? Like, if you have any questions. So before getting into like proper form of cloning and transformation, so I hope you guys have an idea like what is transformation, like why we do it, why bacteria is used as a system for amplification. These things you have the basic idea, or do you want me to like briefly say why? So can anyone say why we do these experiments within bacteria? Like what benefits does bacteria give us while doing cloning experiments? Anyone? Yes, multiply fast, good. So if you have a bacterial cell that multiplies fast, so you'll get your gene of interest in amplified quantities, right? And a very small amount of time, like how approximately it takes 24 hours to grow. Suppose you are giving your plasmid vector today, by tomorrow you'll have many, like the number of cells also you'll have more, and they will multiply as well as the copy number will also increase. So in both the ways, like multiplication within the cell and also multiplication of the cell in two ways. Short reproduction rate because they're good vectors for carriers, good. So you guys have an idea. Good. That's great. So we have just 2 minutes left. I would request you all to just leave the meeting and rejoin the same link. Okay. Is that fine? There's some issues with the Zoom. Like I don't have this. Uh, it's suppose only 40 minutes at a stretch. So I guess you guys will join the session within 2 minutes. Okay. And we can maybe discuss the question there. So many of you had doubts regarding the assignment questions of this last week, I guess. You have submitted, right? Week two submissions have been done, right?
Yes,
Yes,
ma'am.
ma'am.
So you had like this I saw the discussion forum, like your questions regarding the restriction digestion, like the sums or the problems that come with it, right?
Yes, ma'am.
So were you able to solve it or still like it's still in a it's a bit cloudy to you?
We were able to solve it, but it was a bit difficult to understand in the beginning.
Okay. So we'll discuss today. Like I have 3, 4 questions from the assignment as well as some sample questions. We will discuss that. Okay. Okay. So let's begin. We have 4 participants. My screen is visible, right?
Yes, ma'am.
Hmm. So this question that we were discussing. So what could be the answer? Is what is the type of competent cells that is required for a heat shock method? I have two answers. Hmm. B. Okay. So let's see the process of heat shock and a calcium chloride method, like how it happens. Okay. So if I slightly zoom this, I hope it's visible. Okay. So we know that DNA is negatively charged. Why? Because of its phosphate back, right? So as DNA is negatively charged, so it has a negative charge. So and also the cell membrane in the bacteria or the outer membrane, whatever it is present, that is also negatively charged because of the lipid bilayer. Lipid also has phosphate in it, so that is why both of them are negatively charged. Now, negative charge of DNA and negative charge of this membrane will repel each other. So, how will the DNA get in? We need to find a way so that we can actually forge this barrier and get inside. But it is negatively charged. So, what is done is a calcium chloride competent cell is prepared. Now, it's not a calcium, the term competent cell means it's the ability that facilitates or ability to take up the DNA easily and then replicate. So, what is done is prior to like giving the DNA to the cell, it is treated with calcium chloride. Now, calcium chloride is positively charged. So, what is that? It neutralizes the charge of both the DNA as well as the cell wall. So what happens is now because this charge is neutralized, like both of them have zero charge, so they will not repel each other. And when you are performing heat shock on it, this will slightly dislodge from its space. Like you will see small transient or short-lived holes will form through which this will easily go inside. And one more thing happens is because these are neutralized, the DNA calcium, this aggregate, will actually be deposited on the outer layer. So it will stay here, and once the hole is formed, it will easily get in. That is why we use a calcium chloride competent cell for transformation purposes. In case of like bacterial cells. Is it clear? So does anyone have any contradictory statement to it? Like, no, ma'am, this is not the way it is happening. It has some other explanation. Does anyone have any contradiction to it? So I repeat, what are the two things that happen? One is calcium charges neutralizes the both the lipid bilayer as well as the DNA because both of them are negatively charged and they have a tendency to repel each other and move away from the cells, which should be actually the reverse thing, that it should move towards the cell and get inside it. So it neutralizes the charges, and also this complex or the aggregate formed by the calcium and the DNA will sit, or it will be like it will be on the outer covering, and so once we apply heat shock, short-lived holes will form or pores will form, and through it the DNA will get inside. Clear? So generally what is done in our laboratory, like how we perform, how we prepare the cells is uh, we have the cells in a append of tube and we directly place it in a water bath in a high temperature for for a very less amount of time. It gives a heat shock and then we apply the DNA. But keep it in mind, we cannot like put DNA in that directly at that high temperature. That is also a thing. So this temperature balance is done when I hope you guys have you guys performed it in hand? Like have you performed transformation experiments? Any one of you? No. You will, I guess you will in your future. So you'll see that you need to prepare your competent cells, and then you'll be heat shocking it. Then you put the DNA and the calcium chloride. So these things will happen. Generally now things are kit based. Like you have kit, like it's a recipe. Add A, add B, you get this. It's but still you'll understand the process. Like if you go through the protocols and the kits, like the details that comes with the kits, then it'll still be clear to you. I hope you do that and it's clear. Okay. Okay. So till now we have discussed about restriction digestion, how to choose it, how to design primers, and mostly we have discussed about transformation and competent cells and the method of like how heat shock is used. So do you have any questions or do you want some topics to be clarified out of this like from here? We'll see. Let's see. You have submitted your assignment, so we can just go back and see what questions you had this time. Okay. Right. Okay, so you had this question. Anyway, the answer is given here. Like one of the popular methods of transformation of recombinant plasmid to host cells is to perform heat shock transformation. What can be the best explained role of calcium chloride, right? So it imparts a positive charge to the cell wall, right? And why isn't option A and B correct? Like eventually it helps in creating pores in cell membrane to let the plasmid in, or it makes the cell membrane more permeable to accept foreign particles. So why isn't A and B the answer here? Anyone? And why is it like specifically C? Anyone? You guys have answered it, right? You submitted also. So
I
what were
think
you?
it's because you asked specifically the role of calcium chloride. So whatever it does in the beginning, it enables it to do the next steps. So
Yes, very good, very good, very good answer. Because specific. Oh, right. Nidhi, you're also right. Let's go back to the presentation. So yes, the answer was calcium chloride competences. Okay. The next question. Again, it is about it's a trans question from transformation. Okay, so this uh, which of the following methods explain the correct principle of heat shock method of transformation? So you see the three questions that we discussed so far. It actually involves each one step. Initially, it was about type of cells, like about the vector or the plasmid. Now the calcium chloride method, and now we're coming to the heat shock. So just have a look at the question and maybe we can discuss. Hmm. See. Okay. Rest of you, Nidhi has answered. See. Okay. So it's C from all. Now just tell me that why not D? So it is actually we are actually compromising the cell's protective layer by making small pores in it. and that can lead to like the internal components coming out of it. So why not D and why C? Anyone? C, it's not lysis of membrane. Okay. To digest. Okay. Okay. So the catch in these are very straightforward questions, but many a times when we are writing MCQ questions, we often get confused by the terminologies used, like lyse, loosen, digest. Some way or the other, if we are not, now we have like 10-15 minutes, we're discussing every question, but while answering, we often like ignore these specificities in the question. So you see, halt, lyse, loosen, digest, all are somewhere or the other similar if you just read it at a glance. But the catch is, it is a transient change. It's a temporary change. It's not a permanent. Like these holes are temporary. Like just after heat shock, we bring the temperature down. We give a cold. It's not a cold shock, but yeah, we keep it at 0 degrees so that the pores again become normal and they shrink back to the normal. The lipid bilayer gets to the normal thing or its reinstated to its previous version. So we are just giving it a situation where temporarily we are changing or modifying the getup of the cell wall. And after certain time, it will again go back to what it was before. So hence, it is not halting reactions inside. It has nothing to do with reactions inside. It doesn't cause lysis of the cell's protected layer. Lysis is a permanent action. It cannot be reversed back. Like once you lyse the cell layers, it's lysed. It cannot be it is, you cannot reverse it. Loosen, you, yes, you can reverse it, like you loosen the protective layers, which is the cell wall. You let the DNA go in and again you close it. Like heat will open the pores and cold will close the pores. So that is how it happens. And finally, the option D, it's again lyse and digest is almost same. It digests the protective layer, internal components. So the pores might be open for a while, but it is not open for that long that things from inside will come out, right? So definitely, if it is open for a very long time, there could be some passage without any filtration, but no, that doesn't happen because it's like open for a very short period of time. Is it clear? So let's see a picture that what actually happens here. So yes, so this was your DNA. I'll just zoom it up. Yeah. This was your gene of interest. And this is your bacteria. This is its cell wall or cell wall and membrane. This is your cell. Then you are doing calcium treatment to it. What will calcium treatment do? These are the negative charges on the DNA and the negative charges on the membrane. So once you're treating it with calcium, this is being neutralized. And on neutralizing, what happens? On the other hand, you are giving a temperature treatment. So there is a loss of lipids at 0 to 4, from 0 to 42 degree, you do that. Like 0 degree, generally when we are performing any experiments, we keep it on ice. You might have seen your seniors do that. You keep it on ice, right? So from that ice, you just put it on a water bath, which has a temperature set at 42 degrees. So from 0 to 42, this fluctuation, you are you're subjecting the cells to this level of fluctuation. So what happens is, here you see the lipids are like have dislodged, and then through it, the DNA will get in. And once that is done, again you just bring the temperature back to 0 degree, and these pores shrink, and the cell membrane has come back to its original state, but with the DNA has already entered the cell. So that's how calcium treatment and temperature treatment is done. So you can see this is the final, like this is the cell and it has this DNA with it. Clear? Good. You have your explanations. Your explanations are good. Okay. So how many of you actually perform these cloning? Like one of you mentioned you haven't done it. So have any one of you like performed cloning or transformation apart from her, or you just have like passively observed also? Any one of you? Okay, just passively observed. Okay. Okay. Soon you will do it and you'll understand the process much more details once you do it on hand. Okay. Yes, it was option C. So the answer is to loosen the protective layers and let foreign objects go inside the cell. Okay, let's discuss the next question. Okay, so before we get into the next segment, it's mostly about now you have your DNA, now you have amplified it, now you need to observe it. Now that is the part which is this is the downstream of it. Like, okay, your cloning is perfect, your PCR is okay, like your amplification is fine, your cells have the DNA. Now you need to see that actually the DNA is there or no. And that is not just many times it happens that you'll find colonies of cells, but they don't have the target of interest. So how will you know that? So by the process of agarose gel electrophoresis. So what is agarose gel electrophoresis? Agarose is like it's a polymer. It forms a sieve-like of structure. When you solidify it after heating it, through it the DNA passes. You put the DNA in it, the DNA passes. And this, as it passes, we apply electric field to it. And once that electric field is applied, the DNA will resolve or separate according to its size. Like larger DNAs will take more time to pass through the sieve, and smaller size fragments will pass earlier. So this is the principle of agarose gel electrophoresis. Why electrophoresis? Because it's you're applying an electric field to it. So what is actually done? Suppose this is, as you see one here, that this is your DNA sample. Now you have isolated, like from the petri dish, you isolated the colonies, and then you have your sample like this in a Eppendorf tube or in a microcentrifuge tube. So this tube is actually the sample in gel loading buffer. What is said is this is the microcentrifuge tube. So here you have your DNA. What you do is you load it. So by loading, what I mean, there's a cascade-like thing. This is the chamber, okay, and this is your gel. Here, these are the wells. Like literally, these are wells in which you load your DNA, and then you connect it with a power supply. You connect it with a negative and a positive anode, and then you give a electric supply to it, and then there's a buffer through which the ions pass, and there's electricity that generates within it, and what happens is your DNA will get resolved. Now what is like the you have the electric field. Now what is the main concept behind it? This will be a cathode which is a negatively charged, and this is a positively charged. Now why is it like positive above and negative above and positive below and not the reverse? Anyone has any idea that why this is in this way charged? Sorry. Why is the charge of this the cathode and anode in this orientation and not the opposite? Anyone? Phosphate group with negative charge. Good. Yes. So as we discussed, DNA is negatively charged. So in an electric field, can DNA move towards another negative field? No. It will be attracted towards a positive charge or the positive field. DNA is attracted to anode. Good. Very good. So we place the DNA here and we run the gel. By running, I mean to switch on the instrument, the electric field is generated and DNA is dissolved. So as you see here, dissolved. As you see, we have the pink color one is your sample and there's an electric field, and these are your different fragments. And one column will always be a marker DNA. Like what is a marker DNA? It is actually a reference. Like you have different fragments. How will you know what is the size? So you have a marker DNA which has like different fragments in it, and it forms a ladder kind of nature. So suppose this is your fragment, you want to know what is the size, corresponding size of this ladder, you'll see that, and you have your size, like whatever will be the size of this this particular fragment that is your DNA marker will be the size of your fragment that you are analyzing. So that is how it's done. Now, how you observe it? Now, DNA is running through a gel. You cannot see it with your eyes. Like DNA can be seen. It literally cannot be seen. So you have to stain it. So what we do is we stain this entire gel with a dye called ETBR, right? ETBR. So once this is stained and then DNA passes through it, it's an intercalating agent and it will intercalate within the DNA base pairs. So it'll give you a fluorescence color. So once you put this gel, your entire process is done, experiment is done. You pick up this gel and you put it in a UV trans illuminator which has UV light, and you will see pink colored fragments on it. So that is the indication that your experiment was correct and you have your genes or you have your DNA fragments. Clear? Is the concept of agarose gel electrophoresis clear? Clear. You can ask me questions like if you have not performed it and maybe some things are in your mind, then you can ask me questions. Okay. So I assume that you have understood that how the DNA is separated in agarose on applying an electric field to it from, and it moves from a cathode to anode. Okay. So yes, these are so now let's go to the questions. Now, suppose you have a gel like this. Okay. So somebody named Utkarsh had run a agarose gel to check the quality of extracted plasmid, but found that the gel run was shown. He found a gel like this. So, what could be the possible explanation? Like, why such a hazy gel has come like into the picture? Like, what could be the reason? It's hazy, like it's not a very clear gel, I guess. Okay, okay, okay. Good, good, good. Bromophenol was used. Clarify the percentage of agarose used. Okay, I will. Oh, I didn't see the questions. Okay, let's just discuss this and then we might get you to your questions. What do you think? What could have led to this kind of gel? TTBR is not mixed. So, okay. D. Nidhi says, wells are not made properly. Okay, ETBR is not mixed well. Gel not possible. So, why do you think wells were not made properly from the picture? Why do you feel the wells were not made properly? You can mute and also say if it's unmute yourself and like say the answer. The well boundaries don't seem perfect. Okay. Archana, while loading sample, it may overflow. Okay. Don't seem perfect. So Archana and Nidhi are like in favor of the wells. And Rajesh, why do you think that ETBR was not mixed properly? You have given a different answer. Most people are saying
Yes,
four.
ma'am.
Yes.
Yes. Actually, while pouring the agarose gel, na,
Hmm.
it seems the concentration of ETBR is in the final, when we pour, na,
Hmm. Hmm,
it
hmm.
comes, it is not evenly distributed. That is why we
Yes.
got that pinkish color below the
Yes.
gel.
Okay. Okay. So yes, Rajesh is actually correct that ETBR was not mixed well. Before coming to the point that why it was not mixed well, let me just clarify the wells. Why point four is not correct, right? Wells were quite properly made. Like if you see proper rectangles here, right? This is made. It will not be very specific, and once you do it in hand, you'll understand that this is this is a perfectly made well. But when it is coming to fragments, these should be clear. You see, it's a very hazy picture. Once the ETBR has not mixed properly or it has not been added at the right time, these kind of gels you'll find. So I'll just show you how does a perfect gel, like not a perfect gel, but ideal gel look like this. The wells are not here. I've not added the wells here because these wells are okay. Like it will not overflow. Now, why will a gel? You said it could overflow. There's a particular quantity of sample that is added to a gel. Like every well can accommodate that quantity of sample only, and we generally add something lesser than that. So yes, that is not an issue actually. It will not overflow. Generally, it doesn't overflow because that quantity is predetermined. That okay, this gel will have this much. All right. So this is how your agarose gel should look like clean bands like this. This is the ladder, and these are like clean bands. You see thick and clean bands like this. Here also you have bands here. So when ETBR is correctly mixed with a sample, this is with the gel. This is how it looks, and the way properly it is intercalated, and this kind of view you get. So is it clear?
Yes, ma'am.
Yes. So it's most of a technical issue than a biological issue. Like it's mixing was not done properly, so that is why it has happened. And okay, let's discuss the questions that you have. Percentage. First question was clarify the percentage of agarose used. Okay, so as I've said that agarose actually acts like a sieve, which lets the small fragments pass faster and the larger fragments pass slower. Why? Because it has pores within it, right? So higher percentage of agarose that you are using, what will happen is the pore sizes will get smaller, and that will benefit the smaller ones. The smaller fragments will easily pass through it, but the larger ones will not, and it will be like stuck at this position only. But if you like decrease the percentage of your agarose, the pore sizes will actually increase. So all can be resolved. Like you can easily resolve that. So there's no clear definition like what exact percentage. There are different lab standards, different labs use different standards to like determine that what kind of, if you are using, if you have to like a whole not a digested DNA, not a fragmented DNA, then we can go with a lesser percentage. But suppose you have to resolve very smaller fragments, then definitely you have to have a higher agarose percentage, which will give you a better resolution and separation of high molecular weight bands. I guess, is it clear? So if we are using a like higher percentage, smaller bands gets dissolved in a better way, but a lower agarose percentage will give you resolution of like higher molecular weights. Like bigger the size of a fragment, you use like lower the agarose content in it. So it will be a better option for you. Okay. Okay. So somebody also asked me that what is the ideal time we carry out agarose gel electrophoresis? Okay. How do we know the process comes to an end? Good, very good. So you see, it's written 30 to 45 minutes here. What happens is you load your samples and you will see that, and you also load a gel loading buffer. So this gel loading buffer actually is glycerol and some other agents and a dye tool. Okay. So you see, as it increases, there's a dye front, say. Once the dye front has reached this position, we switch off the instrument. So whatever time it takes to like move the diaphragm to move. So what it means that as the diaphragm moves, the DNA is also moving with it because you had added the diaphragm to the sample. So as it moves, but that doesn't quantify, that doesn't signify that it has like it is the position of the DNA. No, it is just the how the samples are running. So that is how we get to know that okay, my run is over. But many a times it happens that we overrun it, like the diaphragm has gone out of the gel and we tend to lose the fragments. So we have to be very careful while running this. What we do is we just stay and keep a observation, like every 15 to 20 minutes we see and see how much the diaphragm has like moved further. And once it has reached like this position, we are sure that okay, this is fine, and then we can stop the instrument. So that's the thing. And also the voltage is a very important thing. We cannot use a very high voltage, like here you see it's 60 to 150 volts. The higher voltage you use, the more heat it generates, and that could actually directly lead to like your DNA can get damaged or your gel can actually disintegrate. These things are issues. So these are like some prescribed, there are some conventions that are followed, but yes, this is one thing. And I guess I had one more question. Ideal time, how do we know why bromophenol blue was used? So I guess this question is clear to you. Why bromophenol blue was used? So there's one more thing about why this bromophenol. It's a very good question that seeing this blue stain kind of thing, you that came to your mind, why bromophenol? So if we many a times these, these dyes have chart that is opposite to DNA or same as DNA. So DNA is negatively charged and this dye, bromophenol blue, is also negatively charged. So both of them will move in the same direction. That is why it is used. But the next question will clear this more, that is why bromophenol is being used. One is to just observe it visually, okay, this is moving to this end, and the second one is like, yes, it is negatively charged, will move along with DNA and not in the opposite direction. Clear? Okay, so that was the answer, that DBR is not mixed properly. Let's go to the next question. It is also from a gel. So again, a person had redone an agarose gel. He just redid that gel and he found that the gel run was like that. This is how he got his gel. So let's interpret what might have been the issue. So that's your answers and we can have a discussion. Okay. Is the question clear to you? That if suppose you perform a gel electrophoresis and you find that you are getting this kind of a gel image. So what can be the explanation? Like what is the possible issue that has led to this kind of a gel? Sorry. Hmm. Okay. So again, that 40-minute timing is over. So we need to leave the meeting and rejoin it in like 2 minutes. So we'll just pick up this question, and that will be the last segment of the discussion. So we'll just pick up the question from where we leave. Okay. Kindly rejoin the meeting once again. 4, 4, 4. Okay, okay. I'll just keep your answers once again. 4. Okay. 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 I hope my screen is visible. So Rajesh has said that option 4 is the correct answer. Wells were not made properly. Okay, the wells are quite unclear here. Fine. Justified. Rest. Rest participants. What is your take on this? That if a gel looks like this, what could be the possible explanation? I guess rest people. Okay, fine. No issues. Okay. So the thing is that, okay. So what generally happens? So generally, gel runs from negative to positive direction, right? You place the DNA here and your gel runs from here. But we know that, not we know, most of you might not be aware of this thing, but ETBR is positively charged. So, and if you like change the electrodes, like you place positive here and negative here, what will happen is your DNA will go out of this well. And as a result, if it goes out of the well, you will not see anything DNA, but you still see that there is a line, there's a straight line here. So why is this line coming? Because we have stained the gel with ETBR and ETBR is positively charged. So by any chance, if you have mistakenly placed the electrodes in the opposite direction, ETBR will flow from this positive to negative direction and it will become here because ETBR is positively charged. So this is the flow of ions from positive to negative. And that is why your DNA, you lose your DNA will go out of here because a negative thing and it's a positive thing. So it will go out of here, but this will form a line here. It will be in the opposite direction to that of the DNA. So the answer is the gel was run from positive electrode to negative. Like you had just changed the electrodes to it. Everything was same. You placed your samples correctly, anything. But the cover that we placed, which has the cathode and anode to it, the cover thing or the electrodes, that was just run from the opposite direction. Clear? Is this clear?
Yes, ma'am.
Right? So this happens
Clear,
many a
clear,
times.
ma'am.
Like this is a very common issue that happens. Like people often tend to forget which electrode they have to connect. So the best thing to remember is negative is black one and the red one is the positive one. So always play like you actually, if you go back to the picture, it looks like this. Yes. Yeah. So this is the instrument, and these places also you see these are marked like with red and black. This is red and this is black. So there's one knob here and there are two knobs that comes out of. You just have to carefully connect black with black and red with red. And similarly, here also you will find a positive mark or a red colored some symbol is there. You just to like carefully place it. And one more thing. Suppose you have placed it here, but the gel was placed in the opposite way. Then also your entire experiment will go in vain. You have to keep it. The well should always face towards the like the head of the well should always be towards the cathode, and the end of the gel should be towards the anode. That is how you make sure. So this is a very common issue that happens. Many people do it. Like it's a very common thing. Okay. So yes, the gel was run from the positive to the negative electrode. Clear? Now coming to the very anticipated discussion of restriction digestion. We'll be discussing this in details, like what actually happens, and I'll be just taking up some very simple examples and we'll be discussing some sums on it. Okay. So yes, is gel electrophoresis still now clear to all of you? Like running the gels in which direction we should run? Are the questions clear? I hope it's clear. Yes, fine. Okay. So let's talk about now. Let's put everything together. We are cloning, we are amplifying, and then we are also running a gel. So this is your plasmid. You have two restriction sites on it, which can be cut by eco R1. Eco R1 is a restriction enzyme. So what happens is two fragments. Suppose you have a circular plasmid and you cut it. Just you forget that there's two eco R1. There's just one cut site. Okay, and you cut it. Then you have just one fragment because it's a circular plasmid. Now, if you have two cut sites, then you have two fragments. So this is the thing that whatever number of cut sites you have, a circular plasmid will always give you the equal number of fragments to it. Okay. So this is a plasmid. You just use a restriction enzyme to cut it and see that if you're not cutting it, if you are just directly observing it in electrophoresis, you will have this uncut. This is a bigger fragment, like this bigger size, like 407 base pairs. Okay. But once you have subjected it to a restriction enzyme, it will have two different fragments to it. Clear? Is it clear?
Yes.
Okay. So what exactly happens? Just let me recapitulate. This is a donor plasmid. It has these two restriction sites on it, and this is a recipient plasmid. So what will happen is you will cut this and put it here. So you are cutting it, that is basically digesting it with these two enzymes, not one and EcoR1. You have this piece of insert, and then you're using the same. If you're cutting something with this, the ends will be like you have sticky ends or like blunt ends to it. They should exactly match the ends where you are going to insert it. So here also you are cutting. You see these are MCS, like multiple cloning sites. We say that different uh, restriction sites they have. You can use any one pair, but ideally we use the same pair for both of these. So you find it here and then you insert it here. Okay, you are using EcoR1 and not to cut it, and then you have inserted it, and then you perform a ligation where you ligate these two, and you have a plasmid which has a gene of interest that was actually inserted with the help of a restriction enzyme, and then this is what is formed. Okay. So now let's just see a very basic example. This is from the internet. It's not part of your assignment, but like a very basic example, like what exactly happens. This is very easy to say, like, okay, in experiments, we are doing Is my screen visible? So yes, I guess we were here. Is my screen visible?
Yes, ma'am.
Okay, okay, okay. So sorry for the inconvenience. I'm extremely sorry. Okay. So this is a question, and the answer is also there. I've just kept it on purpose. On purpose. Yes. So if we see that you have a restriction map, like what is a restriction map? Where you have a you have been given the idea that okay, this is your plasmid, this is the size of the plasmid, and these are your cut sites, like where this enzyme can actually cut. Okay. Now, if we use this map as a guide and give the like, and we are asked that okay, now find the number of fragments along with the lengths that are going to happen or that are going to be formed when you are subjecting this particular plasmid to the enzyme, the restriction enzyme. Okay. So what happens? Now there are two, three things. One is single digest, like you're just digesting this entire thing with a one enzyme. Okay. And there's a combination or a double digestion where you're using two different enzymes to digest this. By digestion, I mean the cutting. Okay. So as you see from, if you just don't ignore the table right now. Here what we see is in this entire fragment, we have BAMH1, BAMH1, BAMH1. Like BAMH1 has three cut sites. So automatically BAMH1 is going to give you three fragments. Clear how why BAMH1 is giving you three fragments. And similarly, EcoR1 has just one cut site, so it will give you one fragment because it will cut the circular plasmid and form a straight fragment. So it will have one. So it's of 20 and 6 kb, 20 kb. And this has three different fragments of BAMH1, 2, 6, and 12. Now, how are the sizes done? Like that you need to find out. See, if EcoR1 cuts it, like entire thing is 20, nothing to do it with that. But BAMH1 cuts it into three fragments. So BAMH1 must cut in places which will overlap with the EcoR1. So if you place one cut site here, one cut site here, and one cut site here, then you have these fragments, which was already told to you. So just directly you have to see, okay, BAMH1, one will be of 4 kb, one will be of 2 kb, one will be of 6 kb, and one will be of 8 kb. When we are considering both BAMH1 and EcoR1. Does that make sense? Does that make sense to all of you? Okay. So how, like by EcoR1, like how the size of fragments are done, and like for a double digestion, what happens? Now, let's get into your assignment question. Can you, okay, 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 sure, 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 Arushi. So the thing is, Arushi, just don't think about the table. Just you focus on this one. What information can you have from here? Like here, this is the plasmid. This is the size of the plasmid, it's a 20 kb. So just why this 20 kb is important, why it is generally given, that whatever restriction digestion enzyme you're using, the fragments that you'll get, if you add up the size of the fragments, you will sum it up to the end total size of the plasmid. That is why this information is in like very important, that what is the total length. Okay. So now, the thing is, that restriction enzymes EcoR1, BAMH1, and a combination of EcoR1 and BAMH1 has been used. So what does that mean? That you are just digesting it only with EcoR1. Okay. Then you are digesting it only with BAMH1. And then you are digesting it with both EcoR1 and BAMH1 at the same time together. Okay. Then what will happen? You see, here you can see that BAMH1 has given you 3 fragments. Like how? If it cuts here, it has one fragment, 1, 2, and 3. And in between, there's one EcoR1, right? So BAMH1 will give you 3 fragments and EcoR1 will give you 1 fragment, because it's a complete, like it's just a single cut. So that's how you decide how it is. So if you see, EcoR1 is giving you a 20 kb fragment because ECO1 has just one cut site. This information was given to you that BAMH1 has 3 cut sites, so it will generate 3 fragments because it's a circular plasmid. If it is cutting at one point, it will have 1 fragment. It gets into a straight thing. And if it is has 2 cut sites, 2 fragments, 3 cut sites, 3 fragments. So from this picture, we can see that EcoR1 has just 1 cut site. So it will give you 1 fragment. And if a plasmid is cut from the between and it generates 1 fragment, it will be the size of the plasmid, whatever the size of the plasmid, that will be the size of the fragment. It will be a fragment now, not an entire plasmid. So yes, it's a 20 kb. So EcoR1 is 20 kb. Now, if we leave the 20 kb aside, now we have to see that if apart from that, if BAMH1 is cutting at 3 different places, what are the 3 different uh, fragments that can form? Now, forget this EcoR1. If this EcoR1 did not exist here, what it would be? BAMH1 had given a 2 kb, a 6 kb, and this entire 1 fragment, which is 4 plus 8, a 12 kb fragment. Clear? So it'll have 3 fragments, 2, 6, 4, and 8. But when we are doing a double digestion or a combination of both EcoR1 and BAMH1, now the EcoR1 we know will cut between this BAMH1. So this 12 kb fragment will be cut from within. It will give you 4 and 8. So that is what is happening. You have 4 fragments. Even if you see 4 cut sites total, irrespective of which enzyme has been used, so 4 fragments you will definitely get. Clear? Okay, that's good. We have 2, 3 more sums on it, so you will be able to understand. Okay, now let's go to the next problem. Chalo. Again, Utkarsh was given a vector of overall length. It's a 20 kb and asked to perform like a restriction digestion. After a single double digestion of 2 enzymes A and B, she obtained the following gel image. Now let me just clarify the question. It's like 3 different experiments were done with the same plasmid. One is where the person had performed the restriction digestion with one enzyme, that is A, then separately with B, and then together in 3 sets. And he saw this was the gel result. Okay. So this is the ladder which says what are your different fragments, and this was your resolved DNA, or the different fragments that you got after performing. So just try to solve what it can be, what could be like the question is given following: ascertain the information that can be obtained about the restriction site. So like you need to find that in this particular plasmid, how many restriction sites do enzyme A and B have. So yes, let's solve it together. Like what could be the possibility? Okay. So why C? Why C? But from the gel image, it's very clear that A has two fragments with, that means two sides, and B has just one fragment, it's with one cut side. So why A three and not two? And A and B four together? How can that be possible? Somebody please explain. B for sure is one, okay, but A and B gives four. A might have two fragments with size. A has two fragments with very good. So let's see. Good. So now let's try to solve it. So this was your 20 kb fragment. Now from the gel, you see that B has one fragment. So it will cut it here. Now you see that A actually has, it shows in its two places, but this 6 kb fragment is a thicker one. So if a particular digestion has same size of fragments, all of them will resolve at the same position. So the band gets thicker there. That means more DNA fragments are there. And you all are absolutely correct that it has two fragments. A has three cut sides in which two fragments are of the same size. So it's like 6 kb, 6 kb. And the other one is like 8 kb, which is cut by the B. So B has one cut side and A has three cut sides in total. Yes. So that the C is the answer. Very good. So A has to be equal 3 as good. Very good. Very good. This gives 4. B1 for sure. All of you were correct in this. That's great. Okay. Let's go to the okay. Let's go to this question. Now, a lot of sums. Now let's slightly change the questions and let's discuss that. Let's come back to cloning once again. So just have a read in this question and we can discuss. So I'll explain the question that you have a vector that is taken as a cloning vector for inserting a gene of interest having a streptomycin resistant gene of its own. And you have a Hint3 cut site that is present on the penicillin resistant gene in the vector. And there's no other antibiotic resistant genes in the vector. Now, Hint3 restriction digestion was performed to insert the gene of interest in the vector. Resultant vectors, after complete transformation in competent cells devoid of any antibiotic resistant gene of its own, are desired recombinant cells were obtained. Which of the following is the desired transformation? So it's a long question, but let's like pictorially depict that what is actually happening. So you have a gene of interest which has a streptomycin resistant gene in it. Okay. So what does a streptomycin resistant gene or a penicillin resistant gene means? That you have this resistant gene in it, and if you subject it to a culture where penicillin is present or streptomycin is present, it will grow because it has this resistant gene and it will provide enzyme to become resistant to it. But if anyway this particular gene is disrupted, then it loses its resistant powers and it will not grow in presence of that antibiotic. Is it clear? Okay, D. Okay. We'll discuss. We are discussing. So your gene of interest has this streptomycin resistant gene. Many people are towards D. Okay, let's see what is it. So, and this vector has the vector also has a penicillin resistant gene, which is also a cut site for Hint. Like if you digested the Hint3, this penicillin resistant gene will get disrupted. So it will lose its resistant power. Okay. So you're doing that. You're exactly doing that. What you're doing? You're actually disrupting it and inserting the streptomycin with Hint3 digestion. So now this recombinant vector is no more penicillin resistant, but yes, it is streptomycin resistant. Because why? The penicillin resistant gene has got disrupted, but it still has the streptomycin resistant gene in it. So when you're growing, what will happen is when you're growing in a streptomycin plate, your colonies will grow because it has the advantage of the streptomycin resistant gene. So your colonies will go. So that brings us to a conclusion that D, Penicillin will not, in penicillin media, it will not survive, but in streptomycin media, it will survive. And all of you were correct. So I hope the explanation is, with the explanation, you are happy with the explanation and the process, and you don't have something in contradiction like any other explanation too. Just tell me that. Yeah. Okay. Okay. So the very anticipated question. This question even came up in the discussion forum, like how to solve it. So the approach towards solving these questions is to just draw it. Last week also somebody asked me, ma'am, how to solve it. I told her to just try drawing it, but I guess there are times when drawings are not enough and we don't understand what is exactly happening. So what the question was, that you were provided with a map of plasmid P300 3000, which size was 15 kb, and you observe that when, while like subjecting it with or digesting it with different combination of restriction enzymes, you have different fragment sizes, like not one, EcoR1, BAMH1, STU1, EcoR1, and STU1 gave these different combinations of fragments. Okay, but if you want to use this combination of BAMH1 and EcoR1, which following fragments would you observe? Like, so it's first thing, it's very clear that you have two fragments. So whatever it will be in two parts. Like the 15 kb will be divided into two parts. So how does the gel look first? You see, not one and EcoR1 has given you a 4 and a 11 kb. But BAMH1 and a STU1 has given you a 9 and 6 kb. Similarly, EcoR1 and STU1 has also given you a 9 and 6 kb. Now the question is, what will BAMH1 and EcoR1 give if they are using this combination? So let's try drawing it first. So this is clear, like BAMH1 and STU1, 6, 9, EcoR1 and STU1, 6 and 9. Now here comes, why have I selected these two first and not one? Whenever you are seeing common fragments, like same way they're resolving, that is the catch to these questions. Like from here, you will get that what will happen with these two. So 9, 6, 9, 6. The thing is, this 6 is common. Like BAM and ECO will be cutting, will have same size fragments, not at the same position. They won't be cutting at the same positions, but they're same size fragments. That is 6 and 6. So if we are using a combination of BAM and EcoR1, they will have a 6 plus 6, 12 kb fragment for sure. Right. Let's see here why. BAMH1 and EcoR1 is here. So it's cutting here. Suppose BAMH1 has one cut side, it will just cut it one place, but you have EcoR1 with it also. So it is like a 12 kb, 6 plus 6. This is common between BAM and ECO. And STU is like 9 kb. It's very clear from here. STU is like 9 kb. This side, if you observe, this is 9. So BAM and ECO one have to be 6 and 6. So it's a 12 kb and the remaining will be a 3 kb band. That is what is happening. And that is also what is there in your answer, this particular combination of 3 and 12. Is this clear to you now? Questions? Okay, I'll repeat. Sure, I'll repeat. So the thing is, when you try to draw it, you see that STU is cutting it here and BAM H1 here. Similarly, ECO and STU, both of them have like same sized fragments. Okay. So we need to find that what is the common size fragment between them. STU is 9. So the rest is 6. So BAM and EcoR1 will at any point of time generate one fragment, which will be 6 plus 6, 12. You just need to add it up because 6 is common between them. 9 goes for 2, so 9 cannot be here, 9 cannot come here, and it has to be like 6 plus 6, 12. So you add it up, and it will give you one entire fragment which will be of 12 kb. And like 15 minus 12 is 3. That is how you deduce that from this figure, that how to derive this. Clear? Oh, very good. Why 9 goes to 2 and not 6? If you see that, if I reverse this, like I place 6 here and 9 here, but we need to find out which is common between BAM and EcoR1. Like if we place 6 here, then that commonness is going. That common part is going. Like if we are placing 9 here, Eco and BAM1 are cutting, like have the same size of fragments. Only then it is possible that these have this common part. Suppose if it was 9, then the common is 9, then what would happen? 9 plus 9, 18, but your fragment, the entire size of your plasmid is 15. So that is exceeding that. So this fragment 6 plus 6, 12 is within 15 kb, and also it is common between the BAMH1 and the EcoR1. Clear, Runal? I guess. Got it, ma'am. Thank you. Archana? So yes, we have some more time left, I guess. Yes. So we can discuss more questions if you have like related to the next assignment, or like any you want some hints for it. Next assignment we cannot discuss right now, but I can just help you with some hints like how to solve it, or maybe this assignment if there was some other question that you were stuck on with. So yes, we can absolutely discuss it. Anything else? Nothing. Okay. So just let me summarize what we have discussed today. We have mostly discussed how to prepare competent cells, like process of restriction digestion in brief, everything in brief, not like in very much details. Then how you find your primers for a PCR reaction. Please explain the first question. Which one, Rajesh?
The first one, actually, joined late, so I missed
Okay,
that.
okay, okay, okay. Sure, sure, sure.
Yes.
I'll just repeat it once. So the first question was mostly about choosing your set of. Okay, just 1 second. I guess we have one more question left. Just, yeah. Yes. So we have one more question. Yes. So the first question was like you have been given a particular vector and also a particular gene, and you need to insert it. So you need to find a set of restriction enzymes to insert that gene of interest within the vector. So what will be your approach, or how will you choose when you've given a question like that? So the explanation to it, you need, if the restriction sites or the map of the vector is given, just try to find a pair of try to find a pair of restriction enzymes which are present in this also, like your options. So that is how you get to know which are going to be there. So here it's like NDEL and HIN3. If you see, these two particular restriction sites are present, plus these enzymes can be easily used to digest it and insert the vector into it. That's how you do it.
Okay,
Clear?
thank you.
Okay.
Yeah, clear.
Yeah. So there's one more question. I guess I missed it. So we can just discuss it quickly. So it's about the PCR, like how what happens in a PCR. So just quickly read this question and we can just have a quick discussion on PCR. So basically, these are the 5 steps of PCR that you need to do. Here he has performed these 5 sets, but after like running the PCR, he found that there was no amplification. Like he did not found any band. There was no band formation. So what could have possibly gone wrong? So for your convenience, I'll just show you the ideal steps of a PCR. So firstly, you need to denature your template DNA, and then you need to reduce the temperature so that your primer anneals, and then again you increase your temperature to a point that you have your DNA synthesis. This is your cycle one, and this completely repeats. And this boy performed the exact thing, but still he did not get any results. So what could possibly be the scenario? Like what went wrong here? Just try to compare these conditions with this one. See, anyone else? Annealing step. The annealing step was not properly performed. If you see the temperature here, okay, the temperature did not go down. It was 72 degrees, like this one. But the annealing should happen below 60 degrees. Otherwise, your they will not they're complementary to bind to that. They have an ideal temperature, and that is like 50 to 60 till 50 to 60 they can bind. But if you like increase the temperature beyond that, it will not complementary bind. It will again like denature. That what is happening in the first and the third step, right? So that is a one more thing, that annealing temperature is very important. You need to provide primers as well as let it anneal to the template strand. If you don't let it anneal, then how will your amplification occur? Yes, D, you were correct. Yeah, D. So I guess that's all for today. It was nice interacting with all of you, and I hope to see you in the future classes also. All these materials will be uploaded in the portal, and you can just have an access to the video as well as my slides. And time to time, if you have any doubts, definitely use the discussion forum to post questions, and we like try to include it in the live sessions. Clear? Is that fine? Okay, okay. Thank you. Thank you so much. Thank you.